Hi there, this is our reverse osmosis part 3. Part 4 is going to be a slideshow. Got a lot of pictures of an RO, makes a little more sense. This one's more on the operations of an RO. We did throw in the B factor, beta factor. This is more of a design factor, but it is important to understand the concept. Is the ratio of the bulk total dissolved solids to the concentration polarization rate. So here's your bulk flow, here's the ratio of concentration, dissolved solids build up. You want this less than 1.2. So basically this means you don't want this 20% higher than your bulk flow. This is what a design factor for ROs. Your normalized flow, we mentioned a few times, it's what the flow should be. It is corrected for temperature, pressure, conductivity. A lot of chemistry analyzers, you want 25 degrees Celsius or 77 degrees Fahrenheit. You can look at the ASTM D4516 standard for this. Good luck with that. It's kind of complicated, and I do believe they charge you for the actual document, but if you're interested in this, the ASTM D4516 will clarify what's involved. Temperature on these is critical. 4 degrees Celsius rise in temperature equals a 10% change in permeate flow. This was done with clean water. It affects the membrane rejection. The higher the pressure, water quality improves. Also, the temperature may cause the membrane to change. The higher temperatures allows more solutes to pass through the membrane. Higher feed water temperature, the pressure decreases, and the higher temperature, permeate total dissolved solids increase. So in the summer months on surface water, you're going to have a little worse permeate, and you'll run a little less pressure for it to run. This is true with a lot of filter systems. You have to change your backwash flow rates in the winter compared to summer. Water's more denser with the cold temperatures. It does affect a lot of items. These are polyamide membranes we've been talking about mostly. They have somewhere between a 200 to 1,000 part per million hour rate for chlorine before the total dissolved solids double. So that's why keeping the chlorine and some of the oxidizing biocides out of these is important. So you can run 1 part per million chlorine for 1,000 hours or 1,000 parts per million for an hour if you do a lot of damage. But the damage is accumulative, so you want to keep chlorine out of these. Use sodium metabisulfites, one chemical used to control free chlorine. You need 1.3 parts per million of metabisulfite for 1 part per million chlorine. The safety factor, you need about 3 parts per million metabisulfite. The product activity, if it's 33%, you'd have to add 6 ppm. These are just kind of hypothetical numbers. The ORP should be between 175 to 200, at least under that. If you have more free chlorine, this number will climb higher. Differential pressure on these is critical. You can only have 15 pounds per square inch or 1 bar pressure per element. Or they recommend 50 psi for multi-elements. If you get higher pressure, you'll collapse the elements, you'll crush them, do a tremendous amount of damage. That's why you can't water hammer reverse osmosis units. You have to start them slowly. High DP can do a lot of damage. Now here's a reverse osmosis drawing. It's a 2-pass unit. See, the stages have taper. This is a 3 to 2. This may have 7 membranes elements, and these may only have 6. Depends on the flow you need to limit the concentration polarization on the membrane. You have to bring in filtered water. Water has to be very clean. You have to pre-treat the water coming into RO. Here you add anti-scale. It goes through a filter. This is critical. Have a DP on it. Downstream of this, you'll add your sodium metabisulfite. You want a little bit of chlorine in the filter to minimize biological growth. That's going to be one of your major problems with these is biological growth in microbes. Then you have a static mixer in the line. Right here you'll check your temperature, conductivity, pressure, the ORP, flow, and pH. If you have a VFD, you'll have the drive will give you the percent, and then you have the downstream pressure. These numbers are all important to track, especially the pressure. If this has to keep driving up to get the same amount of permeate flow, either the temperature changed or you're having a problem in the unit. From here it goes through the first pass, first stage. Comes out of the first pass, you want to check conductivity and pressure. Some people have the luxuries of having transmitters that can track all this data in a control room, or if not, you just may have a pressure gauge and grab samples. But this is important data to collect. It'll tell you if these are starting to foul. You have biological growth or sedimentation or silt building up on these. So if your pressure starts dropping, this has to go higher, you're starting to plug this stage. Then you go to the second stage and goes through this. Then you have your basically a concentrate back pressure valve. This is set for recovery rate. This is set at initial installation and is not touched. If you adjust this, you can change your recovery rate, which may be good, or you may cause scaling in the back of the second stage. And if this gets changed, then your normalization flows through this whole thing or out the window. You don't really know what the shape of your membranes are. They have a bypass around this for when you flush. Here you want to check your flow, conductivity. Some people can check pH. Pressure right here is important. So in all the stages, you want to check the pressure drop on them and the conductivity coming through them, both the permeate and the concentrate. It can help you identify problems. The permeate side, there's check valves in all these. You cannot pressurize the permeate higher than the concentrate. If this pressure is higher on this side, you'll damage your membranes, you'll blow the leaves apart, do a lot of damage to it. So there's check valves. Sometimes I have sample ports on these where you can take a sample off each RO element and look for any problems in the concentration, like a bad brine seal or membrane damage. Comes out of here, permeate. You want to check the pressure and flow. It can be like a rotometer, it can be something just to measure the flow so you can track the flow difference between the stages. Sometimes they have a little pinch valve here for adjusting the permeate flow. If you have one of these, don't touch it. It's probably been preset and you can create a lot of problems by messing with it. Just a word of caution. Don't adjust these valves on the ROs for whatever reason. Here you go to the second stage. Mention that. The big thing is your back pressure control valve. This is set. This determines how much back pressure is on this concentrate side, which determines the recovery, and then also how much permeate you have and how concentrated the wastewater becomes. Your permeate, you can add sodium hydroxide here if you want to get rid of carbon dioxide. The stage is further down. Gases are not taken out with an RO. You have another pump. If it's a VFD, you'll have a percent of the drive on it. Downstream pressure. You go to second pass, first stage. It's pretty similar to the first pass. You have your concentrate flow control valve. This is set for recovery on the second pass. Here you have pressure and conductivity. You check that on downstream at every stage. From here, the water will go to a tank. ROs cannot be backed down very much. Sometimes you might be able to back them down a little bit, but it's better to go to a tank because they're set for a certain flow and you have to run at that. On this one, we'll take the concentrate. It's only reading 63. It's pretty clean water, and we'll send it back into the feed of the first stage. These are just some of the conductivities on a unit like this. You may have 484 micromos or microsiemens of conductivity coming in. You're going to concentrate that to about 578 micromoles after the first stage. After the second stage, you'll be 1300. Your permeate out of the first stage will be a 9.7 micromoles. Second stage will be a 12 because you have higher conductivity coming in. These are taken out a percent of the conductivity. There's a little bit of slip, solute slip or salt slip. So this should be a little bit higher because you're dealing with a little bit higher conductivity water. This can be a big problem in the summertime if your water changes. If you go to well water from surface water and you got a lot higher numbers, it's going to change all this quite a bit. And you could get into a scaling potential. These waters out of here, when combined together, give you about a 10 micromoles. Goes to first stage, 0.47 micromoles coming out. This concentrate up to a 23. Goes to second stage, concentrates up to a 63. You have 0.58 and about a 0.5 micromoles of water coming out. So use the 2-stage if you need cleaner water. And from here, it can go on to other processes to get even cleaner water. Some major problems with running ROs. High pressure can crush membranes, also high temperature and pH. If these things drain down and you hit them with water, they can water hammer, do a lot of damage. Different ion species have different rejection rates. A calcium or magnesium +2 rejects better than a silica. Things like methanol and some of the light organics, they won't reject hardly at all. Gases don't reject. Just remember, Diamond water is very corrosive. You have to use 316 stainless or plastic. Diamond water will pretty much tear about anything up. It's amazing. Okay, this, like I mentioned, these valves are set for recovery rate you don't mess with. These can be adjusted to lower permeate flow from the stage. They're set and left alone. Do not pressurize permeate membrane side. Do not get the permeate higher than the concentrate side or you'll damage the membranes. Normalized permeate drops to 10 to 15%. Do a CIP. Also, if the normalized DP drops to that, you should probably do a CIP. If it goes too far, it may not clean well after that stage. This is set up to flush, which most of these would be. To flush, you need to bring in clean water, Diamond water or permeate water. You can add your biocide. It goes through the first stage, second stage, and there's a bypass around their concentrate recovery valve. So this valve is not adjusted, it drains down. Let's have a drain on your permeate. Once this side is flushed, then you can open the valve here, and then you can flush the second pass with biocide. Biological growths are probably about half the problems with these things of plugging up. So it's a major problem. Even if you have really clean water coming in, there's still a chance you're going to get something in here to start growing. So you need really good feed water treatment, and you need biocides, and you need to flush these every so often to keep from building biological growth in these. When you start them up, there's a question how long they should run to drain. There's a bunch of different numbers. Some people say 20 minutes before you really start getting good data on this, but it seems like it goes a little quicker than that. And it depends what you're using the water for. But when you start up, you do need to flush them down for a little bit. And that concludes this one on RO. Like I say, number 4 will be pictures of RO unit. And then probably 5 will be on cleaning the ROs, doing a CIP and maybe autopsies on the membranes and stuff. Anyhow, that concludes this one. Thank you.